Hello there, my name is Albert. On my channel, I teach and build AI applications to enhance your machine learning, data science, and data analysis skills. Today, we will construct an MRI CNN to detect brain tumors. Artificial intelligence is revolutionizing healthcare in many areas, such as disease diagnosis with medical imaging, surgical robots, and maximizing hospital efficiency. In this case study, we will assume that you work as an AI machine learning consultant and you have been hired by a medical diagnosis company in New York. You have been tasked to improve the speed and accuracy of detecting and localizing brain tumors based on MRI scans. This will drastically reduce the cost of cancer diagnosis and help in early diagnosis of tumors, which will essentially be a lifesaver. The team has collected brain MRI scans and have approached you to develop a model that could detect and localize tumors. You have been provided with 3,000 plus brain MRI scans along with their brain tumor location. In this single video, you will learn how to build a CNN from scratch, leveraging the advantages of using transfer learning from ResNet 50, understand the inner workings of residual networks, and master image segmentation to identify objects at the pixel level. Without much ado, let's get right into coding. To kick off our MRI tumor detection project, let's ensure we have all the necessary libraries and framework installed. Before we do that, let's talk about the folder structure. We have here data_mask.csv, which contains the dataset for the MRI path and other columns that I will elaborate on shortly. We also have the utilities.py file here, which contains some help functions we will be using to train our CNN and our ResUnet. This dataset here contains MRI scans images for both healthy individuals and those with brain tumors. It has the folder name stored as the same as the file path in the data_mask.csv to access these images. And we have ResNet 50-mri.json file, ResUnet MRI, and some other HDF5 files here for the weight, which I will elaborate more on later. Let's open our index.ipynb file and import all these libraries. As we move through this course, I will explain each of the modules uses, but for now, let's just import all of them. Now let's load the data_mask.csv file into a variable. So we create a variable brain_data_frame equals pd.readcsv, then the name of the CSV file, data_mask.csv. So we can type brain_df.head to get us the first 5 rows in the dataset. We have the patient ID, the image path, the max path, and then the max column, which determines whether a brain is having a tumor or not. Next, let's check some basic information about our data set by typing braindf.info. This shows us the data types of all the columns in the data set. The max column indicates the MRI scan results. It shows whether a brain is healthy or affected by a tumor. Let's check the values counts or number of classes in the max column by typing braindf. We select the max column, then we check the value count using the value count function dot index. So this indicates we have two classes, the 0 and 1, which I already explained. The 0 means the brain is having no tumor, and the 1 means the brain is affected by a tumor. Next, we will use Plotly to visualize and interactively explore the distribution of the max values by plotting their count. So we create a new code block and type import plotly.graph objects as go. Figure equals go.figure. Then we type go.bar. We pass in x. The x is going to be the max value count. So we have max dot value count dot index. This is going to get us the 0 and 1 because we have only two classes in this data set. Followed by a y column, which is also going to be the braindf. We select the max column, but we get the values count, the actual count of the classes, the 0 and the 1. Then we type figure dot update traces. We update the traces, which we are going to use a marker color of RGB. We pass in 0, 200 and 0 with a marker line color of an RGB of 0, 255 and 0. Then we have the marker line width to be 7, and finally opacity to be 0.6. Then we type figure.show. This gives us a clear picture of the class numbers. We can see this is interactive. When we hover on this 0 class here, it tells us the number of columns or rows containing this class of 0, same as the one for this one here. How do we access images if you only have reference stored in the dataset? Let's take a look at the max path with braindf.maxpath. This provides for us a list of paths to the max images. In our directory, all the images are renamed to match the path name showed here. To view the max image, we can use the CSV2 module to read the images. So we create a new code block. Then we type plt.imshow. We pass in the CSV2.imRead, which is image read. Then we pass in braindf.maxPath, followed by a square bracket with the number or the row we want to show the image of. So we pass 6 to 3. So this displayed the image of a max found in the dataset. So this is an image of a max. Next, let's print an image of a real MRI scan. We are going to use the same function. So we are going to type image path. We are going to type plt.imshow using the cv2.imRead. Then we pass in the braindf.imagePath. We select the row with number 6 to 3. This shows us a real image of an MRI scan. The max image features only 2 colors. As we can see here, we have the white and black. So to determine the maximum pixel color, we can use the mask method from the cv2 module. So we create a new code block. So we type cv2.imRead. Then we pass in the braindf.themaxPath, followed by a square bracket, then the row that we want to print the maximum or the minimum color from. So 6 2 3 dot mass. This prints for us 225, which represents the color white. To find the minimum pixel color, we do the same thing, just that we are going to replace the max function here with min. So we can copy this, paste it over here, and change this one to min. This gives us 0, indicating a color black. Next, we will visualize the MRI images and max in the dataset separately. So we create a new code block and import random. We create a figure variable and axis. We are going to print them side by side. So we are going to have 2 axes. So we type plt.subplot. We pass in 6 and 2. Then a figure size. Figure size, which is going to be 16,32. We create a variable count equals 0, and for x in range 6, from 0 to 6, we are going to store a random number from 0 to the length of our brain data frame. So we create a variable to hold that. I equals random, using this random module, dot round int, starting from 0 to the length of our brain df data frame. Then we create our axis with the count 0. We give it a title. We set the text to brain MRI. Then we have axis, count. We print the actual image using the img show. Then we type cv2.imread the brain data frame dot image path. We select I. So here we are randomly selecting from all the data frame the length of the data frame starting from 0 and printing a brain MRI scan alongside with its mask. So this is going to print the actual image for us because we are reading from the image path. Next, let's print one for the mask. So we create an axis axs, passing count 0. We passing 1 for the second column. Dot title dot set test. We give it a title of mask. Then we create an axis of count of 1 dot the img show. We pass in the cv2 dot im read with a brain data frame dot the mask path. Then we increase the count by 1. After the loop, we type figure dot tight layout. Here we have the MRI scan alongside with their mask. If there is a tumor, you will see it with its corresponding marks. Otherwise, the marks will be completely black, like these ones here. Now let's plot a brain MRI scan next to a mask image and an MRI with the mask of color red. So we create a new code block. We initialize a count to 0. We create a figure axx equals plt.subplot passing 12 and 3 with a figure size equals 20 by 50. So we have for I in range, length of brain data frame. So if brain df of the mask at the I index is equal to 1 and the count is less than 12, we want to show an image of the brain MRI. So img equals io.imread passing the brain df dot image path with I. axs of count 0 dot title dot set the test to a brain MRI. Then we have axs of count and 0 dot im show with the image. We have a max here, which is io.imread. Pass in the brain data frame dot the mask path of the index I. Then we have axs of count 1, the title, the set test. We give it a name of mask, the title of the plot mask. Then we have axs count 1 dot I'm show max Then finally we print the MRI scan with the color red at where the tumor is located. So img, we look for the mask where the color pixel is 22255. Then we replace it with the color red. We print the image. We give it a title first. Dot set test with mask. We have as of count 2 dot im show img counts plus or equals 1. Then we have figure dot tight layout. So what we are basically doing here is printing the brain MRI scan with the corresponding marks and print a color red at where the mask is located inside the MRI scan. We have an MRI, a mask, and MRI with a mask. Same for the rest of the images. Convolutional neural network is a class of deep feed-forward artificial neural network that works well with image classifications. We have here a CNN architecture called ResNet 50. This is one of the many CNN architecture out there, like ResNet, LeNet 5, VGG, ResNet, and much more. A CNN takes an input like the image we have here, an MRI scan of the brain to detect whether it has a tumor or not. The input image will be processed through a series of layers. In this case of ResNet 50, the input size of the image is 224 by 224 pixels. So this image here is having 224 by 224 pixels. The next layer is zero padding. Padding is added to the input image to allow the convolutional layers to cover the edge of the image properly. In the first stage, we have a convolutional layer which applies filters to the inputs to create a feature map. The feature maps automatically learns from the image for patterns and other features. Batch normalization is applied to normalize the output of the previous layers. This step is to speed up the training and reduce the sensitivity to the network initialization. After the normalization, a ReLU activation function is applied to introduce non-linearity, allowing the network to learn more complex patterns. Mass pooling is used after that to downsample the features map to reduce their dimensions. Let's take a look at the demonstration here for a handwritten recognition problem. When we write one here, it goes through a convolutional layer, then a downsampling, then a convolutional layer, then flattening, and finally a fully connected layer. The convolutional block and identity blocks are the core building blocks of ResNet. The convolutional block typically changes the dimensionality of the input, both in terms of width, height, and depth. And the ID blocks preserve the dimensionality. ResNet 50 uses a special technique called the skip connection or residual connections, which is totally different concept I'll talk about later on. These connections help to address the vanishing gradient problem, which occurs with very deep networks, by allowing the gradient to flow through the network more easily during training. Stage 1 to 5 refers to grouping the convolutional blocks and ID blocks. Each stage may contain multiple blocks, and the number of blocks in each stage can vary. At the last stage, average pooling is applied to reduce the spatial dimensions to 1 by 1, essentially by taking the average of each feature map. The flattened output from the pooling layer is then fed into the fully connected layer, which typically serve as a classifier. The fully connected layer maps the features learned from the network to the desired number of output classes. The final output of the network could be, for example, a classification of the image into one of the several predefined categories. In our case, we have to predict whether there is a brain tumor or not. So it's going to be a binary classification, either 1 or 0. Imagine we have an input, which is the data we are passing through our neural network, represented by X in the diagram. In the traditional neural network, this input would go through several layers, each transforming the data step by step to learn increasingly complex features. Now in ResNet, we introduce something we call residual block, which you see in the diagram has two main paths, the identity path and the main path. The identity path is the shortcut that skips over one or more layers. In the diagram, you see the input X moving along the top and bypassing two layers below. This is where the term identity comes from, because it's the unchanged version of the input, its identity. The main path here goes through transformation by passing through layers, such as convolutional layer, indicated simply as layer in the diagram. In a ResNet, we usually have pairs of convolutions followed by batch normalization and a ReLU activation function. The output of this transformation is represented by f of x, which stands for the function learned by the layers applied to the input x. At the end of the residual block, we combine the output of the main path f of x with the original input x, which has traveled along the identity path. We add them together. This is indicated by the plus sign in a circle. This idea is that f of s learns the residual, or the difference between the input and the desired output. Adding s back in is like saying start with the original information and adjust it based on what we've learned. This structure helps with a common problem in deep neural networks called the vanishing gradient, where the gradient, which tells us how to update our network parameter, gets smaller and smaller as we go through the network during training, making it hard for the early layers to learn. By adding the input x back in after a few layers, we ensure that the gradient can flow through the identity path without diminishing. This helps the network to continue learning even when it's very deep, which is why ResNet can have many layers like ResNet 50 or 100 and still be trained effectively. In summary, a residual block allows network to learn the residuals or changes needed from the input data to get closer to the desired output, and the identity shortcut helps to preserve the gradient through the network. Transfer learning is like giving a head start to your model by using knowledge learned from a different but related task. Imagine if you learn how to play a guitar and now you want to learn how to play ukulele. You can transfer some of your guitar skills to quickly pick up the ukulele. Similarly, we can use a pre-trained neural network that has learned to recognize a variety of features from a large dataset, like ImageNet, and apply it to a new task. Here is how it works in the context of neural networks. You start with a network that has been trained on a large dataset, like ImageNet, to recognize general features in images, such as the edges, textures, and shapes. This network consists of several convolutional layers which act as feature detection, followed by a fully connected layers which classify images based on those features. When you have a new set of image from a different task, for example, a medical image for analysis, instead of starting from the scratch, you can use the pre-trained network. You can remove the original fully connected layer since they were specified to the original task, like classifying animals, and add a new fully connected layers tailored to your specific task, like identifying a healthy versus a diseased tissues. You then train the new network, but only the new layers you've added learn from the new images. The convolutional layers transferred from the pre-trained network can be frozen, so their weights don't change, or they can be fine-tuned, which means they can slightly adjust their weights based on new data. By transferring the learned features from the convolutional layers, you don't need as much as data or training time to achieve a good performance on new tasks, because the network is not learning everything from the scratch. It's leveraging patterns it already knows and applying them to the new images. The result is a model that is customized for your specific task, which, with learned features from original datasets and the ability to classify new images according to your target classes. A ResUnet is a hybrid architecture that combines the ideas of ResNet and UNet for image segmentation tasks. It leverages the strength of ResNet's residual connections and UNet architecture that is particularly good at capturing context and enabling precise localization. The network takes an image as an input and passes it through a successive layers. We have the downsampling path, a convolutional layer 3x3, and a ReLU function. This applies filters to the image to create feature maps, capturing various features such as edges, textures, and more. Each is followed by a ReLU activation function to introduce nonlinearity. The mask pooling layers, indicated as red arrow, reduces the spatial dimensions of the feature maps, effectively downsampling the image and helping the network to capture larger context. A convolutional layer, followed by a mask pool, and another convolutional layer, followed by a mask pool, which goes in that order. This part of the network processes the most abstract representation of the input data, and it's typically where the deepest residual connections are made. The up convolutional layers 2x2 increase the spatial dimensions of the feature maps, effectively upsampling the images, and followed by a concatenation with the corresponding feature map from the downsampling path, known as copy and crop. The copy and crop operation merge the upsampled feature map with a corresponding feature map from the downsampling path, providing a high resolution features for the upsample images. The final layer of the network outputs a segmented map that classifies each pixel of the input image using a 1-by-1 convolution to map the deep feature representation to the desired number of classes. Before we build our convolutional neural network, let's drop the patient ID since it's not needed for our analysis. So we create a new code block. We create brain data frame. Brain data frame underscore train equals brain data frame dot drop with columns of the patient underscore ID. So let's type brain underscore df dot train dot shape to see the shape of this data. So we have roughly about 3,000 plus rows and 3 columns. The patient ID was dropped, so we have 3 columns now. The mask column have to be converted to a string. This will be necessary for using the categorical mode in the flow from data frame. If we omit this step, we will encounter an error later on. So let's create a new code block and type brain df dot train. We select the max equals the brain df underscore train mask column. We apply a lambda function which pick a variable s and stringify everything. So we are stringifying everything inside the mask column, or we are converting everything to a string. Now let's check the updated data info without the patient ID. So brain data frame underscore train dot info. So we have the image path, the mask path, and the mask without the patient ID. We will use the train test plex function from sklearn.model selection to divide our data, allocating 15 for testing and 18 and 85 for training. So from the sklearn module dot model selection, we are going to import train test split. Then we create a variable train test. We pass in the brain data frame with a test size of 0.15. In machine learning, we normally augment the data set for better generalization for the model and prevent overfitting. We are going to use Keras preprocessing image generator to augment our data set. So from Keras preprocessing, we are going to import from Keras preprocessing dot image, we are going to import image generator. We create a new variable data generator equals the image data generator with a res scale of 1.255 and a validation split of 0.15. This rescale here is going to scale the pixel values from the range of 0 to 255 to the range of 0 to 1. This is going to speed up the training process, and this process is usually called normalization. Then we have validation split of 0.15. This tells the data generator to reserve 15% of the image for validation. We are going to create 3 data generators to load our images, one for training, one for validation, and one for testing. So we create a new code block. We have train generator equals datagen dot flow from data frame. We are going to pass in a data frame of train, so meaning this first data generator is going to be for the training data set, and the directory for where the image is located is in the main directory. So we go back and access the images. We give it comma s column, which is going to be the features or the inputs for our model. Here we type image path. Then our y column, which is going to be the output or the predictor for the model, is going to be the mask. So when we pass in an image, we want the model to predict for us the mask, either it is being affected by a brain tumor or not. We have a subset of training, a batch size of 16. This is going to group, or this is going to break down the images into batches to help the algorithm train it more efficiently. We have shuffle to be true. We want to shuffle the data to prevent data abnormality. Then we have a class mode. We have categorical, only if I can spell that right, and a target size of 256, 256. We create a new data generator for the training and testing. So it's basically similar to what we have here. So I'm just going to copy what we have here and change the name to valid generator. So this remains the same, data train directory, same image, and the subset is going to be validation. We have a batch size of 16, true, categorical 256. The rest basically remains the same. We copy this one here, paste it for the second time, and change the variable name to test generator. The rest are going to remain pretty much the same. We are going to change the data frame to test, path same, the S column, Y column. The subset is going to go away. Then we have a batch size, shuffle of false. We don't want to shuffle the test data set because that is what we are going to use to evaluate the model's performance. Everything else remains the same. So let's go ahead and run this code. So we found 2000 plus validated image belonging to 2 classes, 500 for the validation and 590 for the testing. We are going to apply transfer learning by initializing the base model using the ResNet 50 architecture with pre-trained weights from the ImageNet dataset, and transfer these features to our dataset for an optimized and better performing model. So we create a new code block. The base model equals ResNet 50 weights we are going to use the ImageNet. So we pass in ImageNet, comma, include top false, and input tensor is going to be input. We have the shape of 256 by 256 and 3 for the color channel. So this parameter here tells the model to initialize the weights that have been pre-trained on the ImageNet dataset, which consists of millions of images across 1,000 categories. They include top false here. This removes the top layer, allowing us to add our fully connected layer for the MRI task. Let's go ahead and run this. Create a new code block. Then we type base model.summary. Alright, so this gives us a summary for the ResNet 50 CNN architecture. So when we scroll down here, there are 23 million parameters in total, which 23 million of them are trainable parameters, and the model has 53,000 non-trainable parameters, which will not be updated during the training and with their corresponding sizes. Let's freeze all the weights so that we don't update them during the training of our own datasets. This is why we are using transfer learning to leverage the golden features of our ResNet 50 architecture and incorporate our own fully connected neural network for classification. We create a new code block and type for layer in base model.layers. We are looping through all the layers, and we are going to freeze all the trainable parameters. Layers.trainable equals false. Let's create a new code block and create our head model equals the base model dot output. This takes the output of the base model, the one we have up here. Base model, this one here, as the input for this new layers. Then we have head model equals average pooling 2D with a pool size of 4x4 of the head model. So we apply average pooling with a 4x4 window to reduce the spatial dimensions for the feature map. Then we have a head model equals flatten. We give it a name of flatten of the head model. This flattens the pooled feature map into a 1D array to feed into a dense layer. We have another head model which is equal to dense of 256. Activation equals ReLU of the head model. So this add a fully connected dense layer with 256 neurons and a ReLU activation function. Then we have a head model equals dropout 0.3 of the head model. This is also going to apply a dropout with the rate of 0.3 to reduce overfitting by randomly setting a fraction of the input to 0. Then we have a head model equals dense of 256. Activation, we are going to use ReLU, passing the head model. Then we have a head model again equals dropout 0.3. of the head model. Then we add a final dense layer with 2 neurons for the 2 classes. So we are going to have a head model equals dense 2 activation softmax and the head model. We type model equals model, we give it inputs to be the base model dot input, and we give it an output to be the head model. Let's run this code, create a new code block and compile our model. So we have model dot compile with a loss function of categorical entropy, categorical cross entropy, categorical cross entropy. Then we are going to use the Adam optimizer with the metrics of accuracy. Let's run this code. Then we create a new code block, history equals model.fit. We have train generator. Then we have steps per epoch is the train generator dot in divided by 16. We have epochs to be 1, and we have validation data is going to be the validation generator we created initially. Then we have our validation steps to be the valid generator dot in. This will likely take around 10 to 20 minutes depending on the processing power you have. Alright, so it took us 9 minutes 49 seconds for our model to train. We then load a pre-trained neural network model from a JSON file and its corresponding weight from the HDF5 file, and then compiling the model for use in tasks like prediction or further training. So we create a new code block, model underscore JSON equals model dot to JSON. Then with open, we are going to open the classifier ResNet model.json, the classifier ResNet model.json, w as a JSON file. Then we have JSON file dot write. We write the model JSON. We run this code. So next we are going to pre-train the model. We type in with open ResNet 50.mri.json in a write mode as a JSON file. Then we have JSON saved model equals JSON file dot read. Then we load the model by typing model dot tensorflow dot keras dot models from JSON. So we have JSON save model. Then we have the model dot load weight. We are going to load the weight dot hdf5. Then we have model dot compile. Loss function is going to be categorical cross entropy. We are going to use the Adam optimizer and a matrix of accuracy. Now let's evaluate our model using the testing dataset. So we create a new code block. We have test predict equals model dot predict. We use the test generator. We pass in the steps of the test generator dot n divided by of 16. Then we have a verbose of 1. Let's run this code. And wait for a while. Alright, so let's take a look at how the model made predictions on our dataset. So we just simply type in test predict and we have this array here. The first value in each row represents the model's predicted probability that the sample belongs to the first class, and the second value in the row represents the model's probability that the sample belongs to the second class. We know that we want our model to make binary predictions, either a 1 or a 0. To achieve this, we will loop through all the results and use a function called argmax. This function is going to return the index of the maximum number in a list. So in our case, the argmax will return 0 for one line and 1 for the second line. We create a new code block. Then we create a variable predict to hold an empty list. We loop through I in the test predict array. Predict.append string of np.argmax of I. So I is going to be any number from the test predict array. Then we have predict equals np.asArray of predict. Now let's type in predict run this, and we have zeros and ones representing a tumor or no tumor. Let's obtain the accuracy of the model. So we create a variable original, which is going to hold the original predictions for the MRI scans. Then from sklearn.metrics, we are going to import accuracy score. Then we have accuracy equals accuracy score of the original and predict. Then we have accuracy here. So we had 99%, which is a pretty good number, meaning 99% of the time the model gets its predictions right. So we are going to plot a confusion matrix from sklearn.metrics. We are going to import confusion matrix. Then we have CM, short for confusion matrix, to hold the confusion matrix of the original and the predict data sets. Then we plot figure or figure size to be 7 by 7. And using Seaborn, we are going to plot a heat map of the confusion matrix CM with a note of true. The top left cell here, which is the true positive, indicates that for the class label 0, the model correctly predicted 0 for this number of cases. And for the top right cell here, which is the false negative, for the class labeled as 0, the model incorrectly predicted 1 for 0 cases. For the false positive, which is the bottom left cell here, for the class labeled as 1, the model incorrectly predicted 0 for 4 cases. And for the true positive, the class labeled as 1, the model correctly predicted 1 for this number of cases. Let's create a new code block and generate a report for our model. So from sklearn.metrics, we are going to import classification report. Then we have reports here equals classification reports of the original predicts datasets of the labels 0 and 1. Then we print our report. Now we have our model performing very well with detecting the brain tumor and no tumor from the MRI scans. The next question is, how do we identify the exact location of the tumor on the MRI scan if a patient indeed has a tumor? To do this, we have to use a different machine learning approach called image segmentation using the ResUnet architecture. Let's create a new code block and type in braindf underscore mask to get all the MRI which have masks associated with them. So brain df, we have the brain df, we select the mask where the mask is equal to 1. Then we have brain underscore mask the shape. Then we print brain df mask dot head to give us the first 5 rows of the max dataset. So there we have it. We are going to split our data into a train and testing from the sklearn.model selection. We are going to import train test split. We create a variable for strain and validation equals train test split of the brain df mask with the test size 0.15. Then we have a variable for test and validation for the train test splits. We are going to have val, and we are also going to have a test size of 0.5. Next, we create a new code block. We have our train IDs here. We have a list, which is going to be the train dot the image path. Then we have the train mask equals list for the train dot the mask path. Then we have val IDs, which is also going to be list. We have val dot image path and val mask, which is the validation mask, equals list of val dot the mask path. So next, we are going to create an image generator for the validation and the training data. So from utilities, import data generator. Then we have training generator equals data generator of the training IDs and train mask. Then we have our testing. Then we have our validation generator equals the data generator for the validation IDs and the validation mask. So here we notice we have our input as an image and our output as an image. This is unlike the first one we did where we have the images and it's predicting for us a 0 or 1. In this ResUnet architecture, we pass in an image and the output is going to be an image. So the classification is going to happen on the pixel level. So let's create a new code block. Next, we are about to build our ResUnet architecture. And before we start with the ResUnet architecture, we have to build our residual block first. This is the image of the ResUnet, which have res blocks at each level with a mask pooling, followed by another residual block, mask pooling. Then we have our app sampling here, or the app convolution here, followed by a residual block. So we can see we have residual blocks at each stage of the up sampling and down sampling. Let's think of this as building a Lego. We are going to start with the blocks and then connect everything together. So we will first build the residual block, which is this image here. We define a function res block of x, and then f, which is going to be the number of filters. I'll talk more about that later on. Then we create a copy of s equals x. So this input here, x, we create a copy of it because we are going to use one for the main path and one for the identity path. So for the main path, we have x equals a convolutional network, a classic 2D convolutional with the number of filters or kernels f, which we pass in as an argument, with a kernel size of, we have 1 by 1, with strides equals 1 by 1. Then we have our kernel initializer as the he normal. I will post a link inside the description to go read more about the he normal initializer of the x, then followed by a batch normalization, then we have an activation of value, we pass x. So this main path, we are building the blocks. This blocks contains a convolutional 2D for layer 1, a batch normalization, and an activation function. Then it moves on to the next block, which we are going to define. The next block also has a 2D convolution. We pass in f. We have the kernel size, as 1 by 1. So essentially these are basically similar. So I'm going to go ahead and copy this one and paste it here. So we go through, we have the f kernel size of, so the kernel size is going to be a 3 by 3 for this second layer with a stride of 1 by 1. We add a padding to this layer, a padding of same. It has the kernel initializer as he normal. It has a batch normalization and without an activation function. So this is for the main path. X moves through a layer, this one here, then to this layer, this one here, for the main path. Next is the short path. So short path, we use the copy, the one we defined up here, equals a conv 2D network of f. We give it a kernel size equals 1 by 1, strides equals 1 by 1. Then we have a kernel initializer, which is going to be the he normal of the s copy. Then we have s copy of a batch normalization of the s copy. So now we have our short path and main path defined. Let's perform the addition at the output level. So we are going to concat this s coming from or coming through these layers with the identity, the shortcuts or the skip one. So we have s capital X equals add which we are going to add x and s copy. Then we have x activation, which is going to be the ReLU activation function, and s. So finally we are going to return x. So let's run this code and everything is alright. So we are going to create a function for upscaling and concatenating the values passed through it for the ResUnet architecture over here. So we create a new code block. We define a function upsample of concat with s and a residual network. So s equals upsampling 2D of 2 by 2. Then we pass in x. Then we have merge equals concatenate of x and the skip. Then we return the merge. So we are done with the upsampling, this part here, to concatenate the x and the skip blocks. Now let's combine the residual blocks and the upsampling to build the whole architecture to form the ResUnet. This is going to be done in stages. Before that, let's create a new code block. We have the input shape equals 256 by 256, 3. Then we have x input is going to be input of the input shape. So in the first stage, we have a convolutional layer. We have the first convolutional layer. We are building this part here. So we have conv1 underscore in equals conv2d, pass in 16 and 3 with an activation of ReLU, a padding of same, a kernel initializer of he normal of the s input, Then we have conv1 underscore in is also going to have a batch normalization, then it repeats a 2D convolutional. Copy this one, paste it here with a 16 by 3 activation of ReLU, padding of same, the kernel initializer of he normal of the convolutional input. We create another batch normalization, so I copy this and paste it here. Then we have a pool of a mass pooled 2D with a pool size of 2 by 2. As we have here, the mass pool size 2 by 2, so this particular part here of the conv1 in. So we have stage 2, which is going to be conv2 in because a residual block, the function we created initially of poo_1 pass in 32, then we have poo_2 for the second residual block here. _2 is going to be a mass poo2d of poo size 2 by 2 of the convolutional 2 in. Then we move to stage 3, create a conv 3 in, which is going to be have a residual block of poo2 and a 64 filters. Then we have a poo3, which is going to be the mass poo2d with a poo size of 2 by 2. Copy this one, paste it, of the conv3 in. We have stage 4, which are essentially the same but with different variable names. So I'll copy this one, paste it here, change the 3 to 4, this poo to 4, and change this one to 3 of filters 1 to 8. The poo size is going to remain the same, and this side is going to be conv4 in. Then we have the bottleneck this side here. So we have stage 1, 2, 3, and 4. So we are now moving to this part here. When we follow the diagram very well, you can see this is the same thing that we are doing over here. So the bottleneck side is just going to be, so stage 5 is going to be a conv5 in, equals a res block with the poo4 as the input and a filter of 256. So now we are done with the downsampling. Let's move to the upsampling part. So with the upsampling, we are just going to have an upscale stage of 1. This is the first upscale stage. We have up 1, up 1 equals upsample concatenate of the convolution 5 with the convolution 4. Then we have up 1, a residual block of up 1 and 1 to 8 filters. So I'm going to copy this one, paste it for stage 2. We change this to up 2. Then we have here up 1 and conv 3. So we have up 1 and conv 3. Then the residual block for the second stage is going to be 64 filters. We paste same thing for 3, change them. We have up 2 and conv2 in. Then the res block is going to have an up of 3 with filters of 32. We paste 4, change everything here to 4. You have an up sample concat of the up 3 with the convolutional 1 in. So this is going to accept the up 4 and 16 filters. Then we have our final output. Output equals a conv2d 1 by 1 with a padding of same and activation of sigmoid. Of the app4. Then we have model segmentation. We create a variable model segmentation to have or to hold our model. So we have all the inputs as the S inputs and our output to be just the output. So let's run this code. Everything is fine. Let's check the summary of our model by typing model segmentation dot summary. So we have our model summary here. So from utilities, we are going to import focal traverse key. So let's create a new code block. From utilities, we are going to import focal traverse key and this here and this. Create a new code block. Then we compile our model. We have legacy Adam equals tensorflow dot keras dot optimizers dot legacy dot Adam with a learning rate of 0.005 epsilon of 0.1. Then we have model segmentation equals dot compile. We are going to use the optimizer for legacy Adam of a loss of focal traverse key and matrix. We are going to use T vesky. Let's run this. So we are going to use early stopping to exit the training if the validation loss is not decreasing even after certain epochs. So we create a new code block. We have early stopping equals early stopping. We have a monitor to be the validation loss, and we have a mode of mean verbose 1 and save the best only. Save best only equals true. Then we have a check pointer equals the model checkpoint of a file path to be a ResUnet dash weights of HDF5 passing a verbose of 1 and save best only to be true. Let's run this code. Create a new code block and type history equals model segmentation dot fit. We use the train generator. We are going to run this for 1 epochs validation data of the validation generator. Then we use callbacks for the check pointer and early stopping. Let's run this code. This is also going to take some time to train, so let's wait for a while. Alright, so we are done with our training. So let's save the model architecture to a JSON file for future use. Create a new code block, model underscore JSON equals model underscore seg dot to JSON. Then with open ResUnet dash model dot JSON. Write mode as a JSON file. Then we have JSON file dot write model underscore JSON. Let's run this code. So now let's load our model architecture and prepare it for predictions. So we create a new code block from utilities. We're going to import then with open, we are going to open the ResUnet MRI.json in a read mode as a JSON file. Then we have JSON file, JSON underscore save model equals the JSON file dot read. We are essentially reading the model that we saved. Then we load the architecture. We load the model architecture. With model segmentation, model seg tensorflow.keras dot models from JSON. We have JSON saved model. Save model. Then model seg dot load weight. We load the weight underscore seg dot hdf5. Then we have a legacy Adam for our optimizer, tensorflow.keras dot optimizers dot legacy dot Adam with a learning rate of 0.05 and an epsilon of 0.1. So model seg dot compile using the optimizer of legacy Adam and a loss function of focal with a matrix of this. So let's run this code. Alright, so now let's make some predictions. So we create a new code block. From utilities, we are going to import prediction. Then we have image ID, the mask, and has mask equals prediction, which is the test, which accepts the test, accepts the model, and we have the model seg here. So let's run this. The results of this prediction is going to return image ID, the max, and then has a max into these variables. The prediction function is coming from the utilities. So as we wait for this to train or for this to make the predictions, let's check the utility function for the prediction. So we have prediction function here, which accepts a test, a model, and a model seg. Does everything it have to do, like reading the image, normalizing it, reshaping the image, converting it into an array, reshaping the size from 256 by 3 color channels to 1, 256, 256 by 3, and then make the prediction. If tumor is not present, we append the details of the image to the list. And then we read the image, we create an empty array. That's all the logic here, and return the image ID, max, and has max. So we are going to create a data frame for the prediction results. We have df underscore pred, which is going to be pd dot data frame. We are going to have the image path, which is going to be the image ID. Then we have the predicted mask, which is going to be the mask. And then we have has mask, which is going to be has mask. So we have df underscore predict dot head to print the first 5 rows by default if you don't initialize any number here. So we have our image path with the predicted mask, which is an array of an image, and it has the has mask column to tell us whether the image is having a tumor or not. Finally, let's print the brain MRI images alongside with the original images, the AI predicted marks, MRI with original marks, and then the MRI with AI predicted marks. So we create a new code block. Create a variable count equals 0. We have a fig of axs. We have plt.subplot 10,5 of a figure size equals 30 by 50. Then for I in range, we have length of df predict. If df predicts contains a has mask column at the position we are looping through is equal to 1, meaning it has a tumor, and the count is less than 10, we are going to read the image and convert them to RGB format. So we have image equals IO, IM read, we have data frame predict dot image path of I. Then we have image equals CV2 dot CVT color, passing the IMG. Then we have CV2 dot color 2R GB. This one here. We have AXX equals count 0 the title set test. We have the brain MRI. Then we have the ASX count 0 dot IM show of the image. Next, we obtain the max of the image. So max equals IO dot IM read of the data frame predicted max dot the max path of I count 0. This is going to be 1 dot title. Just copy everything here. Let me copy everything here and paste it. So we change this name to original max, and we have IMG. We place the IMG with mask. Then we obtain the predicted max for the image. So we create a variable predicted mask, which is going to be an MP array from NumPy data frame predicts dot predicted mask of I. You have 0 dot squeeze dot round. So basically copying everything here. This has to be 1 1. Then we have 2 here. The title is going to be AI predicted mask, AI predicted mask, and we are going to show the predicted mask. Next, we are going to apply the max to the image, where we have a color channel of 255. We have IMG mask equals 255 equals 255 here, comma 0, comma 0. Then we have AX count 3. Let me just copy here what is here, paste it 3 3, and set the title to MRI with original mask, and show the IMG here, the image. Then copy this one here, this is going to print this. Then we add a new variable, im underscore predicted mask equals 1 equals 0 2 5 5 and 0. Then we have 4 here, and print the title to be MRI with AI predicted mask. Then we update the count plus or equals 1 figure dot tight layout. So what we are basically doing here is to print the brain MRI images alongside with the original marks, the AI predicted marks, the MRI with the original marks, the ground truth, and the MRI with AI predicted mask. This is just beautiful. Thus our AI is able to predict and show on the pixel level where the tumor is. So when we zoom this image, let's just move it right here. We have the brain MRI here, and we have the original mask. We have the original marks. We have the AI predicted marks, the MRI with the original marks, which is the ground truth and what the AI was able to predict. So when we check these images, we can see the AI really did well with its predictions. From what we have here, this is the original marks from the marks images we have with the corresponding MRI scans, and this is what the AI predicted, like essentially the same. This is the marks, and this is what the AI predicted for this image too. This is the marks. This is what the AI predicted on the pixel level, and for all the other images, this is really close to the original marks. I believe you've learned a lot from this tutorial. Now what I want you to do is to transfer these skills to build more projects, or even modify this one to perform much better. I recommend you work on other images like breast cancer or any other image classification tags at the pixel level. If you found this useful, kindly subscribe to my channel. This motivates me to create more content and help build the tech and AI ecosystem. See you in the next one.